our first diffraction calculation will be for single slit Fraunhofer diffraction. This is always where you start. Let's see. So we are going to have a plane wave approach a slit. So I'm going to draw the slit as two opaque barriers, one down here, one here. All right, and the width of the slit is B, like that. So the plane wave goes right through there, right through a slit of width B. One thing that's easy to forget is the slit is actually out of the plane of the board, right? This is the width of the slit. The slit goes out like this. So we actually have a horizontal slit that the light is going through. It's easy to look at this and think of it, forget where the slit is. Okay, the slit is coming out like that. Anyway, slit of width B, and we're gonna think about what does the light do at a screen out here. And as always, we'll focus on some point P on the screen. And we already talked a little bit about how we're going to do this with Haugen's Fresnel principle. We're going to imagine a lot of little point sources in the slit. And let's go ahead and define one as being in the middle of the slit and draw an optical axis like that, going that way. And really what we have to do is think about all these little spherical waves sending light to point P. So for example, we'll have this one make it to point P, and we'll have that one make it to point P. Those two waves. And we got to add those up, keeping up with the interference. Okay? So another name for this is far field diffraction. And by far field, that has a technical meaning in terms of equations, but what it really means is that the light is approximately a plane wave oh my God, it's not a wave on the plane, it's a plane wave at the slit and the screen. So really, the mathematical adjustment we're going to make is that if the light came from some point source out here, we're saying it's a plane by the time it hits the slit. Then we break it into these little spherical wavelets, but they're essentially plane waves by the time they get to point P. So it really is a condition on the width of the slit, the wavelength of the light, and the distance between the screen and the slit, which I haven't labeled here. So we're just going to make those approximations as we go. We're not going to worry about the exact condition that it requires. Okay? So just like with interference, the way we're going to find the intensity or the irradiance at point P is we're going to add it up. Right? So we're going to say the DEP, right, that's the differential electric field at P, is due to one of these little wavelets. So let's see, what does DEP equal? Well, these are actually spherical waves. We haven't talked about spherical waves much, but you can have a spherical wave solution to Maxwell's equations, to the electromagnetic wave equation. And its main difference is that a plane wave, of course, has a planar phase front, and it moves forward with a constant amplitude. A spherical wave has a spherical phase front, and its amplitude has to decrease as it moves out in order to conserve energy. So it really has something that looks like this. We'll call it d E naught over r. That's the amplitude of the wave. And then e to the j kr minus omega t. All right? In that amplitude term, this is called the field amplitude, dE. And it's different from the amplitude of a plane wave. The amplitude of a plane wave is constant, and it has the same units as an electric field, Newton per Coulomb. This field amplitude is actually, it's got the same units of electric field times meters because you have to have somewhat 1 over r here. The amplitude has to go down as you move out. So you might say you should just put the amplitude at the origin, but the amplitude at the origin would be infinity, which doesn't really happen, but when something makes a spherical wave, it looks like it has infinity at the origin. So you can't do that. So basically you figure out what would the electric field be at 1 unit of distance. So if we were doing this in meters, in r, at 1 meter, what would the electric field be? And that value is what is equivalent to the field amplitude. So that's the idea of the field amplitude. Okay? And this is a spherical wave. Okay? So all we got to do is add up the d, e naught, the field amplitude over r, e to the j, kr minus omega t for each one of these, and keep up with the phase differences. Okay. Well, we haven't yet built in the little differential ds, right? So we're going to move around in this slit, and we're going to move along an axis. So we could draw a little axis here like this, the slit axis, and we could say this is the origin of the slit axis. It goes up to b over 2, and it goes to negative b over 2. And if we call this axis s, then little differentials ds move along this axis. So the way we pick off one of our little Haughens wavelets, Haughens Fresnel wavelets, is we talk about something times ds. So again, instead of the field, and instead of the field amplitude, now we are going to go with the field amplitude per unit width. Okay, so that's now called ER, EL times ds over r, e to the j, kr minus omega t, where this is the field amplitude, same concept as over there, per width. Okay, that's the EL. And it's no longer a differential because that's really a value. That's a constant value that exists in the entire slit. It has a certain field amplitude per unit width, and you can divide the width into as small a piece as you want. So now that gets the differential into ds. And that's where we want it, right? Because we're going to actually take an integral. Okay? So next we'll sum it up, and just like always, we just got to figure out what is dE. Well, this is what we're calling dE. Field amplitude per unit width, ds over r, e to the j, kr minus omega t. So that's how you get started.